after conversion, this data is transmitted to a supervised control computer. So the data size will be changed comparing with the existing one. Existing communication message may be sure, but after conversion with XML schema, the data length will be increased. This will cause a change in transmission delay in communication system. The next model is, this is tentative model, that is migration model. Before all the sensors and control systems equip this XML-based conversion mechanism, the supervised control system, this is mainly uses a mainframe of very large and very fluent system in terms of resource and capability. So data is transmitted to supervised control system without change, without conversion to XML system, XML schema. After receiving this data, raw data, if the SEC receives this raw data, then the XML changes happen. The change data will be sent to other users or systems regarding to this process plan. We calculated the data after conversion, XML-based conversion. This table shows obviously the data length will be increased drastically. In worst case, 50 times longer than in the case of 80 byte. The length. This is a simulation result. Simulation result of model 1. The model 1 means XML conversion happens at instruments. The x-axis is the message length, y-axis shows the transmission delay and processing delay. Processing delay means the time requested to convert raw data into XML format. The transmission delay, after the conversion or before the conversion, the data from the instrument to the SEC is the time delay, transmission delay. If you add these two items, this will comprise the communication delay of total in the system. In this table shows that, as is shown in this graph, the transmission or processing delay drastically increased when the data length is more than 8 kilobytes. This graph shows the model 2 delay of simulation model 2. With the result of this simulation, we can analyze the result like this one. Transmission delay. In the case of transmission delay in model 1, longer than existing message without XML conversion. XML conversion message size increased, as I said just before, and the transmission delay depends on message length. But in this case, the processing delay, the transmission delay in model 2 shows no significant change because there is no conversion happens in the instrument level. The processing delay does not happen on traffic load, does not depend on traffic load, and no significant difference is shown between model 1 and model 2. Now, this means that the hardware performance in our test bed, the system simulated the supervised control system computer and the system simulating the instruments has no changes. So the processing delay was no big difference. And processing delay is dependent on the number of segments. The other one is the maximum delay of proposed model was 3 times longer than the existing scheme. The existing scheme is that without XML format conversion. In the worst case, so the proposed scheme may guarantee same performance as existing one when the traffic is less than 7 megabps. This comes from like this one. We use 100 megabps local area network system, and generally in real-time process industry, the total traffic is managed to less than 20% of total bandwidth supported by hardware. So, and in our simulation, the worst case performance was 1/3 of existing one. So in this case, if the total traffic is less than 7 megabps, our proposal, our XML scheme can be applied into real-time industry. The main factor of communication delay was in model 1. In the case of short message, transmission delay was the main factor. In the case of long message, it was processing delay. In model 2, processing delay is the main factor. If the message length is less than 206 bytes, the processing delay is less than about 300 microseconds. I think this can be negligible in your case. Open law may be no significant influence in our simulation and test bed. Conclusion. We proposed the XML schema to represent data of IC instrumentation control system in steel making industries to standardize multi-vendor control and instruments in terms of communication. This system is platform independent and irrelevant to communication protocol and type of devices. And we also verified the performance of proposed design. We proposed two implementation schemes. One can be used in the case of migration state. So after this research, we hand over our research to the real-time industry. And currently, they are considering the application of our research in their plan. That's all. Any question about my presentation?
Yeah, well, thank you. So in the application of instrumentation and control systems, which size of packet is dominant in this application?
Yeah, very good question. Especially in real-time industry, the most of the important data, most of the hard real-time data was very short. For example, according to our investigation of real-time, about 20% is very long data. This is not good. But like 80% is very short, and the cycle is very short. It gets the hard real-time. And another result is 80% of the data is used transmitted in one process. Only 20% will be transferred to other plant or other user. Other user means that the user outside in this plant. Does that answer your question? Any other question, comment? Okay, thank you for your listening. This is the last paper of this session. Sorry for my late in this session. Thank you for joining us. Have a nice day. After this session, we will have some ceremony in second floor. Please participate. That's right.
On the coffee break at second floor, and then after that we have an opening ceremony at 10:10. Yes.
Professor E. John Hall. Okay. So you present about 10 minutes and 5 minutes discussion.
Thank you very much. Good afternoon. I'm going to talk about the analytic performance model of scalar signal processing. The contents are composed of 6 sections. First, the introduction of performance derivation of processor will be discussed. Next, the relation between the window size and interconnect instruction width. Issue width is presented, followed by the analytic performance model. Then the simulated environment and the results are explained, as well as concluding remarks. Currently, the digital signal processor architecture has become more complex proposed the analytic performance model of a superscalar digital signal processor based on the relation between the window size and the instruction issue width. Also, it will utilize the branch predictions, instruction, and data cache misses. For the experiment, 8 UTDSP benchmark programs are used. According to the previous studies, the relation between the window size and the instruction issue width in a dynamically scheduled processor can be shown as I equals alpha times W to the beta, where I is the instruction issue width, W is the window size, and alpha and beta are parameter constants. If we take log of each side, convert it as a linear equation, and use the list in square, we can obtain the alpha and beta values. The alpha and beta values depend not only on the register dependency of a specific benchmark program, which represents its inherent characteristic. If we present the performance in terms of CPI of processor architecture, it can be decomposed as the sum of 4 factors. The CPI steady state can be obtained from the window size and the alpha and beta values, which was previously discussed. Next 3 CPIs are calculated by measuring the number of branch predictions, instruction, and data cache misses. For example, the CPI classified branch prediction can be calculated by multiplying the number of branch predictions and the associated penalty cycles divided by number of instructions. Finally, IPC can be obtained by taking the reciprocal of CPI. Next, the simulation environment is discussed. The superscope instruction set is used for our experiment. The digital signal processor executes instructions out of order with mean of retirement. The instructions are shown to have unit delay latency with the unbounded number of functional units. 5 different sizes of window ranging from 4 to 64 is employed. And on the right side, you can see the simulation flow. UTDSP benchmarks are compiled and fed into shape, which generates instruction traces. The instruction trace is used for the simulator input, obtaining alpha and beta values and performance measurement. Eight UTDSP benchmarks from FFT to LPC are used for our experiment. 10 million instructions of each benchmark are utilized for the simulation. Next here is the statistical profile of the instruction class. We can see that the integer and load instructions take a larger portion of the instruction class. It also contains instructions such as store, branch, and floating point instructions. The next figure is the curve showing the relation of the instruction window size and the instruction issue width. The next figure is a curve showing the relation of the instruction window size and its performance in log scale. We can see that the relation is quite linear up to the window size of 32, which corresponds to 5 because of its low scale. But beyond window size of 64, the linearity slows down because the instruction parallelism is restricted in the basic block boundary. As previously mentioned, the alpha and beta values are obtained using the least mean square technique. On the right side, you can see the table which shows alpha and beta values obtained from each benchmark. These values represent the inherent characteristic of each DSP benchmark program. Lastly, the bar graph shows the performance of each benchmark calculated by the analytic model and the performance measured by the trace value simulation. The left bar represented as white color is the major performance by the transparent simulation, and the black bar on the right side is the performance calculated by the proposing analytic model. You can see that the two graphs have similar values and the same tendency. For the window size of 32, which is represented at the left side, the error is within 2.9% with an average error of 0.9%. And for the right side, this is the simulation. And for the right side, this is the simulation result with the window size of 64. The performance has increased, and in the case of window size 32, the accuracy has been degraded a little bit, but still achieves the average mean error of 7.7%, which is less than 10% of error. So now I'd like to give concluding remarks. I have developed an analytical performance model of a superscalar digital signal processor based on the window size and instruction width. For the window size of 16, 32, and 64, the average error results within 5%, which is quite accurate. For the future works, I'm planning to improve the model with the limited issue width, the non-unit latency of instructions, and the limited number of functional units to adapt more to the real application case. So this is my presentation, and is there any question?
Thank you very much, Professor Lee, for your presentation. So, to audience, do you have any questions or comments? Okay, can you show me two slides before? You said alpha and okay. So then use alpha and beta. What's the meaning and what's the significant value? What's you should know different value. So what's the meaning?